Welcome back. So let's pick up where we left off. We were talking about energy consumption, and we were discussing where what sectors consume the most energy, and what the largest sources of energy production were. So let's look at just one more graph on energy production, and this one is looking at energy consumption by sector over time. So I'd like to focus on the graph on the left. And I like these graphs because they give us a historical perspective of which sector has been consuming what amount of energy, and the agency attempts to predict a future consumption of energy by all of these sectors. So on the top line we have just electrical power, and we can see that historically this has gone up, and it projects that hopefully that will even out in the next 30 years or so. Second, we have industrial energy, so I guess they're predicting that that is going to go up over time, looking into the future. And transportation hopefully will dip down, so that is good news that hopefully we will adopt more energy efficient methods, and that we'll be able to reduce consumption of energy for the purpose of transportation. On the right side, we are looking at what type of fuel is fueling all of these different types of energy consumption. So it looks like natural gas kind of is one that jumps out, where we have the blue line. We see over time we've increased our natural gas consumption, and they're projecting that we are going to continue that trend of increasing natural gas consumption. On the flip side, we have coal on the gray line, which is actually going down in terms of consumption, and it looks like they predict that that will continue to stay down. So that is happy news, since burning coal for the purpose of producing energy can release a lot of toxic compounds and a lot of air pollution into the environment. And one of the things that we've talked about previously is acid rain. So of course you can go back to that lecture and review that if you need to, but you might want to remind yourself of why burning coal contributes to acid rain. Okay, so do you remember the second law of thermodynamics? If not, this would be a great time for you to pause the video and go back and review it. Just a quick refresher. So we know that when we convert energy from one form to another, so for example, when we convert fossil fuels to electricity, we're not going to get the same amount of energy on either side of the equation. So if we take a certain amount of fossil fuels that in theory should produce this much electricity, we're actually going to find that the amount of electricity that is produced is much lower, and that is because a lot of it's being lost to the system as we burn the fossil fuels to create the energy. So there's a lot of inefficiencies in the extraction of energy, and scientists and engineers and physicists are trying to develop methods of reducing these inefficiencies. So when we look at fossil fuels, we can calculate pretty much with a lot of precision how much energy we can expect from a certain amount of fossil fuels, and calculate how inefficient that process is. And we can improve infrastructure to generate electricity, as well as improve other steps in that pathway to improve our to enhance the efficiency by which we gather electricity from certain resources. And this will make these resources go farther, so we'll require less of these resources to produce the same amount of electricity. And let's just take a look at some of the ways in which we're losing energy along the way. So transportation of these fossil fuels or other elements around obviously is going to cost energy, right? We're going to have to invest gasoline into moving the fossil fuels around, and processing of the fossil fuels takes a lot of energy. And the process of combusting them to produce the electricity itself is actually quite lossy, and we're going to lose a lot of energy to the system during that process. And just moving electricity around after the fact is going to also result in some losses. So what is the efficiency of some of these processes? Most coal burning power plants are about 35% efficient, so we're working on improving those numbers, like I said. And if you were to go become an engineer, you could work on this problem yourself. Um, Power plants using other fossil fuels could be more efficient, and in some cases, combining natural gas with other things can achieve almost a 60% efficiency, so that is pretty remarkable, something to strive for. So nowadays we're using non-renewable energy sources to produce a lot of our electricity and our transportation. So this includes fossil fuels, and which include coal and oil and things like that. So let's take a look at that breakdown. So here is the fuel source over time, starting at 1971 and going up until 2012, I believe. So we can see that coal is the major source of producing energy, and it's been pretty consistently the major source. Oil has reduced a little bit, so we've reduced our consumption of oil for the purpose of producing energy. We've increased our consumption of natural gas, and up on the very top in yellow we have other renewables such as solar and wind, and excluding hydro, so hydro is in blue. So we'd like to increase that yellow, the width of that yellow line there, and increase our dependence on renewable sources. Let's talk about non-renewable energy sources. So if you have a gas consuming car, you put gasoline in your car, and that is a fossil fuel, and was originated from fossil fuels. So fossil fuels encompass any coal, oil, natural gases, a lot of these things that we've been talking about for a lot of the lecture. And non-renewable energy also encompasses nuclear energy, which is I think it's about 10% of electricity is generated that way, so it's not a massive source of generating energy, but it is considerable. So what are fossil fuels? Where did they come from? Think back to our lecture about carbon and how we are a carbon-based life, and recall that most things are made out of carbon. So our proteins, our fats, our carbohydrates are all largely dependent on carbon as the backbone of the molecules. And fossil fuels are actually made out of this carbon, this organic material. So anything that lived millions of years ago and at some point died and went into the ground in some form became a layer of organic material in the ground, and this material underwent different physical processes, and some of them were compressed more than others. Some of them just stayed underground and decayed in different ways. But the point is that this material is very carbon rich, and that makes it contain a lot of energy, and we can burn it and release this energy. So most of the coal, oil, and natural gases are formed from biomass of ancient organisms that died about 50 to 350 million years ago. And it needs to be that old because that's how long these processes took to occur. So coal is which is the primary source of producing electricity in the United States currently. So it's formed from the remains of trees and other vegetation about 300 million years ago. And there are 4 different types of coal. I don't want you to necessarily remember the differences between all these different types, but look at this diagram and understand where coal comes from and what processes brought it about. So it's again, it's organic material that's somewhere underground, and different processes occurred, and it created these different forms of coal that we as human beings come back now and excavate this coal out of the ground. And if you recall, so peat is that form on the very left, so it is the least condensed form of coal, and we've talked about peat a little bit in the very first lecture, that organic, that carbon-rich material that is underground and how people burn it as a source of fuel and energy and other methods. So we've just so this is just another picture of peat that might remind you of the lecture we had previously. Here's a coal mine. So human beings have been since they discovered coal was underground, have been building these excavation tunnels. So you can dig out coal from above ground as well if you just dig a really big hole, but sometimes we build underground tunnels and excavate the coal that is there. And you might have seen references to this in popular culture that might look familiar. So we burn the coal to produce electricity, and coal is what we use primarily now. And here are some reasons why we'd like to move away from using coal as a method of generating electricity or energy in general. So coal contains a lot of impurities, and when we burn them, these impurities go into the air and it releases mercury, lead, and arsenic into the air that you're breathing. And that is can be toxic to human beings and other forms of life. And the other thing that coal releases when it burns is sulfur dioxide. So take a moment. Can you figure out what effect releasing sulfur dioxide will have if we burn coal and release it into the atmosphere? Do you remember what that might cause? And finally, so all of these organic materials are very carbon rich, like we've been saying, and that's what makes them burn so well, and that's what makes them such a ideal fuel, because they contain all that energy. However, because they are full of carbon, when we burn them, they actually release the carbon into the air in the form of CO2, and that contributes to there being more CO2 or carbon dioxide in the atmosphere. And we're going to talk about what that leads to, I think, in the next class. But just as a primer, as an introduction to this class, when you have excessive carbon dioxide in the atmosphere from burning all of these fossil fuels, it prevents infrared radiation from leaving the surface of the Earth and going into the atmosphere. So it ends up actually warming up the planet, and this is occurring to a level that is going to change the distribution of water and a lot of different other things, and which is going to have a pretty impactful effect on life as we know it. So what are some advantages of coal? Of course, there's a reason why we use it so frequently. It's very energy dense. There's a lot of it. I guess it's relatively easy to obtain, and it's cheap. So that's always a good plus. Petroleum also originated from organic material. In this case, it's ocean-dwelling phytoplankton that died and sank down to the bottom of the ocean and decompose and turn into this organic sludge that we like to isolate and purify and then use to burn in our engines and in other ways. So petroleum is a hydrocarbon. Again, there's that word carbon that's coming back, so we know it's carbon rich, right? It's organic material, and burning carbon releases a lot of energy. So here's a picture of a cartoon of where oil is under the ground. And they're showing you that there's an oil rig on top that's digging down and removing that oil from the ground and bringing it up to the surface where it's harvesting it. And they're also showing you that natural gas, in this particular case, exists above that oil area, and that natural gas is also isolated under these conditions, and we use that as well. So there's the chemical name of natural gas, and I think in that case it's methane. CH4 is methane, and there's your C, there's your carbon. C is for carbon. And what are some advantages of using petroleum? So again, it releases carbon dioxide into the atmosphere. So what does carbon dioxide released into the atmosphere do? It leads to Earth getting warmer. Another big disadvantage of using petroleum is that frequently we lose control of containing this oil. So we take all this oil out of the ground. We need millions and millions of gallons of it, and many times we've actually lost control of that and caused a lot of oil to leak into either bodies of water or other environments that have had a pretty terrible impact on local animals and humans as well when that oil gets released into water or into the ecosystem. So furthermore, there are other toxic chemicals that are released when oil is burned. So what are some advantages? It burns a little bit cleaner, it's easy to transport, and it's very energy dense. So those are the advantages of using petroleum. Of course, moving back to the disadvantage, one incident that might be in your memory was the Deepwater Horizon oil spill. So this was a BP rig that some accidents happened, but also it turned out some lack of regulation, and they didn't follow some of the rules about about taking proper precautions to prevent this from happening. But there was a catastrophic event, and as a result, the well wasn't capped for a bit, and a pretty significant amount of oil spilled into the ocean. So here's a map of a lot of these incidents. So it's showing you the big red dot in the center there is the Deepwater Horizon event. So the size of the circle is demonstrating how much oil was spilled into the ecosystem. So they're showing you millions of gallons spilled. So the Deepwater Horizon had about 134 million gallons of oil spilling into the ocean. So that had a pretty catastrophic effect on the ecosystem, and we saw that when the oil came up on shore, but I'm sure there were a lot of other effects that we didn't observe because they happened underwater. And you can see from the map that these are just some of the biggest spills that happened in recent history, and that they happen not infrequently. So we are causing a lot of negative impacts by spilling oil accidentally when we extract it. So in the middle, in the large picture, they're showing you a relatively smaller oil leak. So here's a Shell well, and it leaked 88,000 gallons. So there you can see the widespread effect of all of that oil leaking into the water. So recall that the BP leak was 134 million gallons, so that was significantly more than what you're seeing up here. And I just put a couple pictures on top of wildlife being affected by this oil, so it is quite deadly when they interact with it. And here's just a little infographic of a relatively small spill. So it was a tanker carrying oil around the Delaware River, somewhere around Philadelphia, hit a pretty big anchor that was buried underground in the riverbed, and they didn't see it, or they didn't know it was there, and they hit it, and it tore open the hull of the ship. And it released 263,000 gallons of heavy oil, which by some standards would not be considered a massive spill. However, let's look at the quantifications they made of the impact that had, both economically and on the environment, to the extent that they could measure. So starting from the top, they estimate that 260,000 gallons of oil spilled. Then they're giving you the weight of the anchor. That's not entirely relevant for the story, but they estimate that 11,500 birds were killed. So those are just the animals that they can actually measure. They had to completely close the river down, so the effect of the oil spill was too catastrophic, and they could not allow more boats to pass through. And there was also a nuclear plant upstream or downstream, I'm not really sure actually, but they had to shut that down because that was affected by the pollution in the water. Perhaps the nuclear plant was using water for cooling or something, and they couldn't anymore because of the oil contamination. So they estimate that led to a economic hit of about 33 million. Now, so it oiled all of the shores, and then the state was given another 30 million to try to repair the damage. Whether or not that was sufficient is impossible to know, but regardless of the efforts that they took to improve it, of course, there was some impact that occurred before they could even do anything about it. And so again, that's a pretty small oil spill. So that's something that was so small it probably never even reached the news. And so that gives you an idea of what kind of impact these oil spills have on local economies and local wildlife. Okay, so natural gas, remember that was in that pocket above the oil, which we saw in that cartoon earlier. So it exists as a component of petroleum in the ground. There are also other gaseous deposits that are only natural gas and don't have petroleum in them as well. They're mostly methane and then some other gases. So what are some advantages of using natural gas? It burns relatively cleanly, so it doesn't produce a lot of pollution and electricity into the it doesn't produce a lot of pollution into the environment, and it releases a lot less carbon into the environment than coal. So those are both good advantages. Potentially, excavating for the purpose of isolating natural gas can contaminate groundwater, and any unburned natural gas goes into the atmosphere, and we don't want methane in the atmosphere. That's considered also a environmental pollution. So those are the major types of fossil fuels that we utilize to create energy. And I just want to bring up one additional point, because this is going to be relevant later on, is that fossil fuels, in addition to generating energy, also generate plastic. So this is going to be the topic of a lecture later on, and I hope this piqued your interest. All right, so fossil fuels are a finite resource. There's only so much gasoline and coal. There's only so much oil and coal that is present on Earth. And at some point, we are going to deplete these resources, and there's not going to be anything left. There's not going to be any fossil fuels available to burn anymore. Now, we're also increasing our energy consumption. So think back to the graphs that we saw in the beginning of the lecture, and we saw all of those lines going up of all our energy consumption, largely because the size of our population is increasing, also because there are countries that are still in the process of becoming industrialized and developing. So those countries, we might predict that some of the people there might ramp up their energy use per capita to levels that might be similar to what Americans use. So if everyone had the energy consumption of an American, we'd actually run out of fossil fuels pretty soon. So we have a lot of demand for producing energy and a limited number of resources to do so. And this is thinking back to our per capita energy use. What is kind of nice about this, and we saw this earlier, is that our per capita energy use has pretty much leveled out. So this allows us to make predictions of how long these fossil fuels are going to last. So if we assume, well, here's what every person on Earth is going to use per year or per day or per unit time, then we can guess how long these fossil fuels are going to last. And somebody named Hubbert actually did so. So he made a calculation of how much energy every person is going to use. He made a prediction looking forward into the future of what that quantity might be. And he also made some educated guesses about what the quantity of fossil fuels we have present on Earth are. And he did a thorough investigation of all the resources we have now and what sort of geographical and geological conditions they were in, and he looked at all of the geological conditions on Earth and said, well, here's the amount of resources we probably have. So he made as accurate as he could of a guess of how many fossil fuels we had, and then took into account how fast we're using these fossil fuels, and drew a curve of when we were going to run out of these resources. So, what he's showing you here is let's look at the orange curve, for example. Over time, the orange curve is going to go up, and that is representative of how much oil production we're utilizing to convert into energy. And we might think of ourselves somewhere in this phase right here, right? So when we looked at those graphs in the beginning of the lecture, we saw oil production going up, 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 so we might be somewhere here. And that oil production is going to ramp up if we continue on with the behavior that we are demonstrating now. And at some point we're going to deplete those resources. So we're going to hit the amount, we're going to hit the, when the well runs dry, we're going to hit the end of those resources. And then we're going to have to reduce oil production because there won't be any left to excavate. So oil or coal, and these terms rather interchangeably. Okay, and so that's the curve he drew, and you can put years on this if you like, and we have actually calculated that. What's kind of interesting about this curve is that the two lines here are showing you the range of estimates that he made. So we don't know exactly how much fossil fuels are on Earth, because some deposits are still undiscovered. Some oil deposits are still undiscovered, but let's look at the upper range and the lower range of how much oil could possibly be on Earth. So the blue range is the lower estimate. So that's if we make all our calculations and we say this is the low range of how much oil is present on Earth, and the orange line is the upper estimate. So what's interesting that Hubert found was that even if you take into account this upper limit and lower limit, we're still going to run out of oil at about the same time. So having that upper estimate doesn't increase the amount of time we have with fossil fuels, because people, being the flawed species that we are just going to increase our oil production, use it more rapidly, and then run out sooner. So, what are our estimates? If current global use continues, we will run out of conventional oil in less than 40 years. That's their estimates. Coal is probably going to last a little bit longer, so maybe we have 200 years of that. So some of you, if you're lucky, are going to potentially see the end of the availability of fossil fuels as we know them. So imagine life going from your grandparents not having anything but a radio to entertain them to the lifestyle that we have today, where we're surrounded by iPads and iPhones and all kinds of technology, to a life where we might not have fossil fuels for transportation, for generating electricity, and all of the other things that we require fossil fuels for. So ponder that before you go on to the next part of the lecture.